So, Assalamu alaikum everyone. So, in the previous session, we started our discussions with the four fundamental subspaces. So, in that, we had a row space, we had a column space, we had a null space of A and null space of A transpose. So, this was under the assumption that we had a matrix A. And for that, these things exist. There are four subspaces that we started. So, the first thing that we told about these subspaces is that so when we had that matrix A in which we tried to make it in a row reduced echelon form. I think the matrix was 1 1 1 and it was 2 1 2, then 3 2 3, then 1 1 1. This was our matrix A. So in this the question now we want to answer about these subspaces, the dimensions and the bases. So if you now reduce this into row reduced echelon form, okay, the first thing that we'll do is, so we got something like this 1 0 0 1 and then I think 1 1 0 0 0 0 0 0, something like this. I don't exactly remember, but I hope this was the thing that we got. This was the row reduced echelon form.
Sir, please change its color. It's not visible on screen.
Okay.
Yes.
So what I'm saying is that when we reduce this A into row reduced echelon form, so what we got out of this, we got 0 1 1 0 and it was followed by zeros. This whole row became 0 and then we had I guess 1 1 and then 0 1, something like this. Let's suppose it was this, otherwise we can back check it as well. So this was what we got. So on the question now is that we had these four spaces: row space, null space of A, column space, and column space of not null space of A transpose. So the two things that we have to find is bases, and then we have to find dimensions. These are the two things that we want to find for all of these subspaces. As it was previously clear, I think you have also revised these lectures, and we got to know this row space has a dimension of R. So these are the dimensions, and these are also dimensions. The first thing we saw is that the vectors that are in row space, so they belong to Rn. And similar for this null space of A. Similarly for this column space, the vectors belong to Rm. And for this null space of A transpose, we called it also as a left null space. So for that, the vectors also were in Rm. So the dimensions of a column space, if we speak. So how do we get the column space? So the column space of A basically is the linear combination of these columns. So if you want to find the basis, the first thing is we reduce into row reduced echelon form. So there are only two pivots left. So what is that telling us? That thing is telling us that I think this should be 1001 here. It is 1001. So what this thing is telling us that if there are only two pivot columns left, that means that we have two rows, two columns are sufficient to get everything that exists in the column space. So if I somebody tells me that what is the basis of this A matrix, so what I can say is that I can take just two vectors. So basis column space of A, the basis of that is 1 1 1 and 2 1 2. These are the two vectors that exist in basis. So these two vectors span the whole column space of A. As you know that I can get this 3 2 3 just by adding the first and the second column. By just adding these two, so I can get this third. Now this fourth column, I can get it directly from the first column. And linear combination of any of these things can be directly achieved by taking the linear combination of these two columns. So this is the basis. So I told you the definition of dimension is that how many vectors are there in basis. So there are two vectors. So it is pretty much clear that dimension is 2 for this column space, for the column space of A. So you saw that the dimension of column space of A was equal to 2. And we know that this 2 also was equal to the number of pivots. So this is also equal to number of pivots. That is equal to rank. That's how we got this R, the dimension R for this column space. Similarly, if we want to get the null space out of it, so how did we construct the null space? So for null space, we had something called as free variables. So in that, how many free variables were there? So free variables were a total, there were, for example, n columns. So out of n, r were pivot. So n minus r were the free variables, and we constructed the null space by using this n minus r variables. So that's how we got this n minus r. Okay, and it's easy to construct bases. Just take those columns, fill the values by 1 0, and the other in the second iteration for these free variables have 0 1 value, and then you'll easily get the basis of this null space. Similarly, you can do for the row space as well. So the amazing thing is that the row space and the column space has both dimensions r, which is equal to the rank, because we have just flipped these rows. So what column space of A is, so you are having A and you are taking the column space. Row space means you're just transposing the matrix. If you call column space of A transpose, that's what I mean by this row space. I hope that it's easy to conclude that R and M minus R, how we got it here, if you understood this part. Then I also told you a very important thing. I told you that column space of A, when we reduce into the row reduced echelon form, so now we had column space of A, it is not equal to the column space of row reduced echelon form. So when you sort of had this matrix, this is row reduced echelon form of this matrix in which we performed the elementary transformations. So I told you that before this there was some column space of A. This is not equal to the column space of this row reduced echelon form because it got changed somehow. So now this vector is not reachable. So whatever the vectors were present in the column space of A, they are not the vectors present in column space of R, column space of this row reduced echelon form. But one amazing thing was that row space of A is equal to row space of this row reduced echelon form. This was equal because how? The thing is, if we want to get any row, so we got this transformation by performing some elementary operations. You can just undo these elementary operations, just reverse these elementary operations in order to land this at again. So here, what is the basis? If you tell me what is the basis of this row space, so I'll tell you the first two vectors. So these are the first two rows, they are the basis. So you can, by the combination of these, you can get the any vector basically. Okay, so you have to like I don't think this row reduced echelon form is exact here, so but you can get it. So and here one row became total 0. So for that I told you that this row, if it became 0, this is the row which became 0 basically. So we're left with these two rows. So these two rows become our basis. So let me find the exact thing that we got in the column we got in this row reduced echelon form, so that it is coherent with the lecture. So what was that? If I have written it somewhere, I think it was, yes, it was 100111. It's 1 here. So here it was 1. So this is I think, yeah, this is exact. So this is our row reduced echelon form of this matrix. So what we found is basis of column space of A, that's these two columns are the basis. For the null space, I told you that there are two pivot and two free variables. For those, just in the first pivot variable, in the first free variable, put these 1 zeros and you will get these values A1, B1 something. And then the other vector, put 0, 1 in the free variables and then get this A2, B2, and these will be the basis. Okay, for the null space, and the dimension also will be equal to 2. So here, because this is R and this is n minus R. So here we can also write that dimension of null space of A is equal to 2, because n minus R is 2. It's total 4. 4 minus 2 is 2. So here it's n minus R. Similarly, for this row space, if you want to get the basis for this row space, so basis vectors for this row space are now these two vectors. The first row of this row reduced echelon form and the second row of this row reduced echelon form. These are the basis. So if you write the basis, so you can just write that. And then for this A transpose, similarly you have transpose a matrix. So for that, if you want to find this null space of A transpose, okay, so how you can do that? To find this null space, you have to transpose the matrix. So basically what you have to do is, if our matrix was 1 1 1 2 1 2 3 3 3 3 2 3, sorry, 3 2 3 and 1 1 1, if this was our matrix, so we got some row reduced echelon form into this. So as you know that one of the whole rows became 0. Okay, one of the rows became 0. So this was our 0 1 1 0. So 1 1 1 0. So this is what we got. So if you just keep the track of these operations, as you know that if you when we learned to found the inverse, so what we did is whatever elementary transformation we performed, we sort of captured that into a matrix. So that can be done here. So we can just put a matrix E here. Okay, so if you see that identity when we are trying to find the inverse, so we had this matrix A, then we had this matrix I. Okay, so we performed some operations E onto this matrix. So this matrix got changed into something else, and this matrix also got changed into something else. So we keep track of this E matrix. E matrix basically is the operations that we did onto this matrix so as to get this matrix. Okay, so in the inverse case, we made this matrix as I. So that's why we said that as this EA and it became equal to I. So this matrix became equal to I. So we said that this E is the inverse of this matrix. So we said that A inverse is equal to E basically then. So but here these matrices are not like perfectly invertible, as you see that the dependence in the columns, but still we can have this E matrix over here. Okay, this E matrix will define the operations that we performed on this matrix so as to get this matrix. So I'll just keep track of this zeros, how we got these zeros. How we got these zeros basically is, if you take one of this, if you take none of this and zero of this, so I can write 1, 0 and -1, something like this. So you see that we'll get this zero as 0, because I told you that in the matrix multiplication the rows of this are linear combination of rows of this. Okay, so by taking the linear combination, I'll take 1 times the first row, 0 times the second row, and -1 times the third row. This is how that will give me 0. Okay, so this is the vector that will be present in the, this is the vector that will be present in the null space of this null space of A transpose. So again we can have one more vector. So we can have a vector like this. So we can have a vector -1, 0, 1. This is also in the null space of A transpose, because basically Ax is equal to B, Ax is equal to 0. So whatever values I can give to A, I can give to this X, that belongs to the null space. I am just trying to do one thing. I am trying to find the basis and I am trying to find the dimensions. Is it clear? Like, can you find the basis and the dimensions now? Because I have given you like enough ideas to find the dimensions.
Yes, sir.
Okay. Nice. So this is the thing that I want you to get into head, just summarizing these subspaces. So I made this picture in a certain way because we are going to use this somehow. Okay, so how we are going to, first I'll tell you why is this called a left null space. Why is this called left null space? So if you say that A transpose of y is equal to 0, that's the meaning of the null space of A transpose. So what I can do is, if I transpose whole of this matrix, so if I transpose whole of this matrix, so this is A transpose y is equal to 0, that's what I said, null space of A. So what I'm saying is, if I transpose this portion now, so what I'll get is, I'll get A transpose y whole transpose and 0 transpose. So if the zeros were written like this, now we'll write zeros like this. This is the meaning of transpose on zeros. So if you expand this, I told you that if we have A B whole transpose, that is equal to B transpose A transpose, if you remember this property about transposes. Okay, so now we get A transpose transpose and Y transpose in the end. So here you know that again a property, A transpose transpose is equal to A. So here you get YT A is equal to 0. So you saw that this now is in the left side of this A. That's why it's called left null space. So I told you that it's called as left null space. So did you saw why it's called left null space? Because A is not now transposed. So you can just put this row at the left side. And again, as we had this Ax is equal to 0, now we have Y transpose A is equal to 0. So here this is right null space, and now we have this left null space. All the values of Y transpose, which will basically make this equation equal to 0. Is it clear why is it called left null space?
Yes, sir.
Okay.
Okay.
So now we'll move ahead. The important thing that we have discussed basically today is that of linear regression. Okay, that's the thing we want to discuss. Let me again just as you saw this vector spaces, we can have for example, we can have vector space R2, we can have vector space R3, we can also have vector spaces like R m cross n. So what is the meaning of that? Let's suppose we have a 3 cross 3 matrix. So this will be R 3 cross 3. Okay, so what is important in the vector space? We should have the basis, and basis should span the whole space, and they should follow the property of that linear combination. And if you take 3 cross 3 matrices, they should belong in this. So if you have a matrix A B C D E F G H I, okay, so this is the matrix, this is the 3 cross 3 matrix. So if you take any 3 cross 3 matrix, 1 1 1 2 1 2 3 4 3, this is one matrix, random matrix. If you take some other matrix, 3 4 3 1 2 4 8 9 6 8 6 9 something, and if you add these two matrices, you know that still it will be a 3 cross 3 matrix. And even if you multiply this matrix with any number, so you'll still get a 3 cross 3 matrix. So what I'm saying by that is that this basically is a vector space. So if you have a matrix 3 cross 3 matrix, that's why these vectors are also these sort of vectors are also vector spaces. These are 3 cross 3. So what will the basis for this? So if you want to find the basis, as you have 9 entries for this, so the basis will be like this: 1 0 0 0 0 0, so 0 0 0, comma then we'll put 1 at second entry, and then everything will be 0, and there will be 9 elements in the basis. If you see, what's the meaning of basis? Basically, we want to get every possible vector in the vector space. For that, as we have this vector space of 3 cross 3 matrices, so we have this 3 cross 3 matrices. Now you can take any linear combination. If you want to find this a b c d e f g h I, this one, so you can just multiply this with a and then with b, so this entry will get changed into a, this will get changed into b, again at the end this entry will get changed into I. So this is how you will get this a b c d e f. So this I'll call as standard basis. Standard basis for what? Standard basis for R 3 cross 3. So what will be the subspaces for this? So what will be the subspaces for this R 3 cross 3? So the first thing is diagonal matrices. So if we had diagonal matrices like this, A, B, C, then we'll have zeros and zeros over here. So this also is a vector space itself. Okay, so what will the basis for this? So basis will be 1, 0, 0, 0, 0, 0, 0, 0, 0, and other vector in the base will be 1. So this will be other vector, and one more will be there, 0, 0, 1, 0, 0. So this will be the other vectors. So this is also a vector space. So now we have this bigger vector space of 3 cross 3 matrices. So this will be a subspace. So matrix of diagonal matrix. So diagonal matrix. This it will be subspace of this R 3 cross 3 matrix. So then we'll have maybe upper triangular matrices. Upper triangular matrices. They'll also be subspaces. So what I am trying to sort of convey here is, it is not necessary that you will only have this R2, R3, R4 as vector spaces. So this R3 cross 4 or Rm cross n will be also as a vector space. They'll be treated as a vector spaces. That's how maths now generalizes it. So what maths does is, so it will say that even you need not to, it's not compulsory that you have the elements as real values here, as we had these 1, 2, 3, 4, 5, 6, 7, 8, 9, something like this. So we can have any element in here. So we call those elements of field elements. Okay, so we'll represent that field with F. Okay, and then it will have its own rows and columns. So F m cross n. So this can be a vector space. Now F, it can be a number, it can be anything else. So if you guys are interested in cryptography and things like that, so there you will get to know about these fields a lot. So there you will make a field, and this basically is called as abstract algebra. Abstract algebra. Okay, and sometimes they call it modern algebra as well. So they basically generalize this the whole of this that we studied for this R and m cross n. And just for your information, this modern algebra is considered one of the toughest topics in IAS mathematics. Why is it considered as one of the toughest topics? Because of these things, because they have to read about these rings, fields, groups, abelian groups and stuff like that. And it is not taught in undergrad level. I think it is taught for in some courses, but for the majority of the portions, this modern algebra is not taught in +1, +2. But this basically is just an extension of this linear algebra that we saw, that we had this R, and then in the R we'll replace it by the field and operation. Basically there we don't have this plus and dot, we have some other operations. So still they are represented by this plus and dot, but we still call them addition, but they behave differently. So now it is established that we can have different types of vector spaces. Our focus here was on these. We had these real numbers as the entries in the vector spaces, and they were having some particular like rows and columns. Can I move forward now? Is it clear that vector space are not just restricted to this R2, R3 and Rn, but they can be like matrices, they can be a bunch of other things as well. Is it clear?
Yes, sir.
Okay. Now let's move on to the really important topic that I actually want to convey. So now the topic of linear regression will start. Grab some water and we'll connect every dot in order to understand this linear regression. So after this, I want you guys to feel that we can code this linear regression from scratch without importing anything. That's because whole of this algorithm is based on these matrices. Okay. So what is this linear regression? So let me give you a bigger picture first. The bigger picture is that, let's suppose we'll solve this problem in 2D first, then we can solve it in 3D. Suppose we have some points given to us. So we have some points given to us like this. So let's suppose this is 1, 2, and 3. This is 1, 2, and 3. So let's suppose I have a point here, 1, 1. This is 1 point. 1, 2, 3, 1, 2, and 3. And let's suppose I have another point 3, 3 over here. This is my other point. And let's suppose I have 3, 2, some other point like right here. 3, 2, something over here. Okay, so as you see that these 3 points are non-collinear. Non-collinear basically means that they don't lie on the same line. Collinear means if they lie on the same line. So these 3 points are collinear. So if you see, you cannot pass, you can basically pass one line from these 2 points, but this point is left out. So what we try to do is we try to basically fit the best line. So this is called as curve fitting. Okay, so we try to fit the best line so that the error is minimized. So what is the meaning of error? So that it seems like that maybe we're not able to pass a line through all the points. Maybe this line can be a plane as well in 3D, so it can be hyperplane in 4D. So how many our dimensions we have? So but what we'll do is we'll try to approximate it. We'll see what is the best thing that we can do. So if you speak mathematically, so there are some points like ax is equal, there are equations for which we want to find answers. So let's suppose here we have these variables called c and call them c and d. So this equation basically can be written as like this. For this equation 1 so I can write y plus, let's suppose I have to fit basically this 1 So this is my x coordinate and this is my y coordinate. So you know that y is equal to mx plus c. So this is the thing I want to make sure this point lies on that line. So let me just abstract it out first so that it is not boring for you guys. So what I'm saying is that, so we'll have, for these 3 points we'll have 3 equations. And you have 3 equations but 2 unknowns. So 2 unknowns are c and d. These are our 2 unknowns. Okay, so if you look at that perspective, so it is a problem of linear algebra. So we are basically solving the equations. So basically you have to find c and d such that you will just draw a line so that there will be this line will be the best fit. Why is it called regression? So why is it called regression? The point here is that, so you will get some value. For example, for this, if you have a point over here 2.5, so when you sort of plot this line and you get this line, so here you will get some corresponding value of this over here. Okay, so there I told you that in the classification problem we have some problems as binary classification, in which we have classes 0 and 1. We have multi-class classification, in which we had 0 to k classes, 0 1 2 3 4 till k classes. But there is a problem of regression as well. Regression takes real number values. So where is this seen, this regression problem? So if you take, let's suppose you want to let's suppose predict house prices. So the features that you have been given is, let's suppose square footage of the house, how much house is bigger, and the second thing that is about the locality of the house, in which locality the house is there. So let's suppose this is C and this is D. Now based on these two features, you want to predict the prices. You want to predict, so what will be the price of the house? Okay. Now you have these data points. So you have a lot of data points over here. So in this, for example, let's say I just took 3 data points. Let's suppose you had some data points over here. So what you will try to do is you will try to fit this line. You will try to fit a line in such a way, because you know that these points will be non-collinear. These points, some points will be like this. These points will be like this. So you'll have to try to fit a line so that this is the best approximation of this. Maybe there will be some error here and there, but the whole problem is that you will have to find a line such that, so that when you plot this line and when you get this regression out of it, there will be very less error. So here if you see that this is error, so we'll find for this point we'll find the value over here, but there is this small error over here. So but this error can be manageable. So we want to try to minimize the error. So by fitting this best fit line. So is the problem of linear regression clear? What linear regression tries to do? Then we'll go into the mathematical details of how it is done. Is it clear first?
Yes, sir.
So what linear regression tries to do is that it tries to fit a best line. It's called linear regression. Why? Because we will use some linear surface. Either it will be a line if we have only 2 features. If the features are greater than 2, 3, so we'll use hyperplanes. We'll use, if features are 3, we'll use a plane. If features are, let's suppose 10, we'll use a 9-dimensional plane. So that we cannot visualize. But now algebra gives the power to solve this, to find this best fit line. So the only problem that we have to is we have to find the C and D. Let's suppose we have these equations like this. So we had, let's suppose 2c plus 3 is equal to 2c plus 3d is equal to 4, something like this. 4c plus 9d is equal to 6. 3c plus 6d is equal to, let's suppose, 5. These are the equations we have to solve. Now you can see that we have more number of equations here and less number of variables. So we have equations, there are 3 equations and there are only 2 unknowns. So all the solutions won't be possible here. So as you know that in ax is equal to b now. So now we have m is greater than n. So number of equations is greater than number of variables. And we want to find the value of these variables, which will be giving these values. Basically we want to find the column space of A. But you know that this vector, let's suppose it's called B. This B may not be in the column space of A because we have this property. Okay, what we want to do is, so we want to find some a x hat is equal some p. Okay, this is what we want to find. Our job was to find this, but we know that there is no solution, let's suppose, for this b, because you know that these equations are more than the number of variables. So now what is the best chance we can have? The best thing that we can do is we can solve some a x hat is equal p, because this p lies in the column space of a. As you know that this b may not always lie in the column space. If it is lying in the column space, then we will have a line passing through that b directly. But here if you see that when it does not lie, so what will happen is we'll try to solve this equation under a condition. What should be the condition? The condition should be that this ax minus b, this is some error, because we have to find ax is equal b. That means ax minus b is equal to 0. That was our condition. But what we cannot do this now. As I said that this b does not fall in the column space of a. This is not there in the column space of a. So what I can do is I can find ax hat is equal to p under the condition that ax minus b, this should be very minimum. This should be minimum. Now I translate the linear regression problem into a mathematical problem. So regression problem is this problem. So we have to fit a line. So given that given the value of these points, we have to fit the best fit curve. So that was our job. Our job is to find a line which is the best fit for these. Now you know that if these points were in the column space of A, then it will be easy for us to solve the equation. Let's suppose if we had this equation like this, suppose 1 1 1 2 1 2, something like this. So let's suppose this is our x, c and d, and now this is our a and abc. Let's suppose it is 3 2 3. Now you can see this column, this vector lies in the column space of this a. This is a, this is our x, and this is our b. Now you know that this b belongs to column space of a. Why? Because I can just take c is equal to 1 and d is equal to 1. That's what I can take, and I can get to this. But now I know that it is not possible for every b that this c and d will exist. Let's suppose I'll take some random things. I'll take 4 8 9. Okay, so now you cannot solve this equation. So here we have a is equal to have 3 equations, 2 unknowns, and you need to solve for this, and you cannot take any linear combination in order to get this. Okay, so now this b, sometimes b, and most of the times b won't belong to this c of a. Okay, as you know that why won't it, because it is a 3-dimensional vector. So at least there should be 3 independent vectors if you want to get every vector. So if you want to get every vector, there should be 3 3-dimensional vectors. Now you see that here we have only 2 vectors. So it is a sure game that in a 3D plane, in a 3D this R3 will just span a plane, and maybe sometimes this vector may not be present in the plane of these two. It may not be present in the span of these two vectors that are given here. Okay, so in that way, what are we trying to do is we are trying to solve ax hat is equal to p. We are trying to find a vector p which is closest to b. Okay, such that this is what we try to find, such that this ax minus b which we try to find, it should be equal to 0 ideally. But we now know that this cannot be solved. This ax is equal to b cannot be solved now, because b does not lie in the column space of a. So what we should do is we will find some p which basically lies in this column space of a, but under a condition that ax minus b, this should be minimized. Is the mathematical model of this problem clear? Is it clear now? Now we'll move on to what is called as orthogonal vectors and orthogonal subspaces. Okay, this is what we'll see. So if you've seen the previous lectures, we started with this orthogonal vectors. What is the meaning of this orthogonal? So if the vectors are at the angle of 90 degrees, that's we call them as orthogonal vectors. Let's suppose we have this vector v1 and we have this vector, suppose v2. These are the two vectors. So this is our vector v1 plus v2. Okay, so this is the 90-degree angle. So in terms of mathematics, what you saw that in terms of dot product, we saw that if we take this v1 transpose v2, this should be equal to 0. That's the meaning of orthogonality. That is, dot product of these of two orthogonal vectors is equal to 0. Let's see this. Let's go back to the old Pythagoras and see how to prove that. How to prove this. Now we have this base and this is perpendicular, this hypotenuse. So we can write base square plus perpendicular square. This basically is equal to the hypotenuse square. Okay, so I can write this like this: v1 transpose v. Okay, so just let me justify this. How can I write this? So as you know that, let's suppose we have a vector 1 2 3. Okay, so I can write the dot product of this vector as 1 2 3 multiplied by 1 2 3. So this will give me the basically square of this vector. Let's call this vector A. This will be A transpose, this will be A. Okay, and this will be 1 square plus 2 square plus 3 square. This will be equal to 9. 4 is equal to 13. 14. This will be equal to 14. I think that this is why we can write this like this, and it's clear to you. So now that this V transpose V can be written like this, then we can write this V2 transpose V like this. This should be equal to V1 plus V2 transpose V1 plus V2. Okay, this is V1 transpose V. Now if we sort of expand this, so this will be equal to V1 transpose V1 plus V1 transpose V2 plus V2 transpose V1 plus V2 transpose V2. This is equal to V1 transpose V1 and V2 transpose V2. If you see, these two things will cancel out. This will cancel out with this with this. Now we are left with these two. And now these two basically things are one the similar. Let me give you an example to justify this. Let's suppose we have vector x that's equal to 1 2 3, and we have some vector y that's equal to 1 1 4, something like this. So if you can perform xt y, that basically means 1 2 3 multiplied by 1 1 4. This is equal to 1 square plus 2 plus 3 4 12, so that's equal to 15. Similarly, if you can do y transpose x, that basically means 1 1 4 multiplied by x, that's 1 2 3. This is equal to 1 square again plus 2 plus 12, that's again equal to 15. So now I can write both of these things as one. So I can write, so just erasing this much. I think this is pretty clear. So how are these two things now equal? So what I can write is, I can write 2 times v1 transpose v2 is equal to 0. So this basically means v1 transpose v2 is equal to 0. That's why by using Pythagoras theorem, I tried to prove why is this dot product equal to 0. I hope this is clear. Now we want to see when are the two subspaces. Now we have a vector space in which we have subspaces, and for these subspaces we want to see when are they actually orthogonal. So when are two subspaces orthogonal? Let's suppose we have a subspace V and we have a subspace W. So I'll write it here. So when are two of these? So if every vector in V is orthogonal to every vector of W, that time we'll call that as these two V and W, they are orthogonal to each other, these two subspaces. Let's take an example. In R3, we'll take an example. Let's suppose we have a subspace, like for example like this. Okay, so we have a subspace like this, and then maybe some other subspace like this. Can we say these two are orthogonal? I hope that you will agree with me that these two are not orthogonal. Why? Because for example we have vector over here, it's like this, and then on this subspace we will have a vector like this. So here the angle is more than 90 degree. I think this is not orthogonal, so you cannot call it orthogonal. Okay, so what I'm telling you is that if we have a vector space, let's suppose that's in R3, and that vector space can have subspaces within it. This wall is one subspace and maybe floor is in the subspace. Okay, these are two subspaces. So can we say, are these orthogonal vectors? So are these orthogonal subspaces? Let's suppose, because plane is a vector space, and the plane is also a vector. Let's suppose this is like this. These are two planes that we had. This is, let's suppose, wall, and this is floor, because they lie in R3 and these are two subspaces. So what do you say? Are these orthogonal to each other?
Yes, sir.
Okay. So what I told you is that every vector in here should be orthogonal to every vector in here. So if I take a vector like this, and if I take a vector like this, so do you think that these are orthogonal? Is there a 90 degree angle between these two? This angle is not 90. Clearly it is visible from here. If you just take this wall and the floor, I can take two different vectors where the angle will not be 90 degrees. So these two are not orthogonal subspaces to each other. Is it clear? Is it clear why are these not orthogonal? Just see, this is your wall and this is your floor. Okay, so what I'm saying is that if you take, let's suppose, a vector like this, because this vector now belongs to, let's suppose, your wall, and then we have a vector which is like this, let's suppose a vector like this. Now you saw that the angle is greater than 90, it's not 90 degree. I told you in the definition, I told you that every vector in V must be perpendicular to every vector in W. So here you saw that I just give you an example. So this vector is not perpendicular to this vector. That means these two are not orthogonal subspace to each other. Is it clear now? Or do you have any doubt?
Yes, sir.
Okay. So for the orthogonality, any vector should be, that's why I gave you the example of this. So if I have this is also a subspace. The line is also a subspace. This is also a subspace. Now you can take a vector like this on this line, and you can take a vector on, let's suppose, this on this line. So here you will see it's 90 degree angle. So every vector here will be basically orthogonal to every other vector. So let's suppose this is V and this is W. Every vector in V will be orthogonal to this vector W. Is it clear?
Yes, sir.
Okay. So now you have this concept of orthogonality. Now we will see what is the relation between these null spaces, this picture basically. This is the picture. Okay. And we want to see what is the relation between these subspaces with each other. Okay. As they also are subspaces. So I want to see what is the relation between these things together. Let's now again paste this picture over here. This is the picture. Now this is our column space. Okay, this is our column space, and this is our row space. Let's suppose this is our row space. Let's first see. So row space is basically, if we have an equation ax is equal to something b. So we are saying the combination of all the rows of A, C of A. Whatever vectors are we able to get by the combination of vectors, by the combination of these vectors present in A, that's called as column space. Okay, and how is null space defined? So null space basically is defined that every vector x which takes this A to 0, that is the null space of A. Okay, if we write this A, so this A has, let's suppose, row 1, row 2 till row n. Okay, then we have some x, let's suppose this is equal to 0. So A x is equal to 0. So what I am claiming is, I am saying you that row space is orthogonal to null space. Okay, so this is my claim. Now I want to show you that these two things are perpendicular to each other. So how I'm claiming you that is that because you know that if I have to take A, if I have a vector A and I have another vector B, so in order these two to be orthogonal, A transpose B should be equal to 0. This is what I have to show. So now I have this vector, I have this A and I have this x. You know that if I take this row 1, okay, if I multiply with this whole x, I'll get the 0 entry. So that means I have this row 1 multiplied by whole of the x. Okay, so that will give me 0. So that means this row 1 is perpendicular to vectors in x. So any row, now if we for example now multiply this row 2 with this x, similarly this will be equal to 0, because that's what this equation ax is equal to b is telling us. Take any row, multiply with the column of x, that will give us 0. So can I claim now that these rows are basically perpendicular to any vector that's in column space? Can I claim this, that if I take any row among these rows and I multiply with any vector that takes the whole matrix to 0, these rows are perpendicular to those x's? Amir, can I tell you this? Can I basically make this claim? That is, I'll
Yes,
take
sir.
any other row, I'll multiply it with x, I'll take it as, this basically takes it to 0. Similarly, now if I take any linear combination of these rows, let's suppose I'll take C1 of row 1, okay, and then I'll multiply it with the whole x. This will also be equal to 0. So any linear combination of these rows, this vector will basically take it to 0. So that's what I had to prove. So in order to prove this, I had to tell you that the whole of this whatever the vector is possible because of these vectors. If that vector is multiplied by this x, that should take it to 0. That's the definition of orthogonality. So if you take any vector, random vector A, and if you multiply it with any vector B, and if A transpose B is equal to 0, then we say that these two vectors basically are orthogonal to each other. That's what I have shown here. So you take any linear combination of these rows and you multiply it with any of the x, it will give you basically 0. That's why I'm saying that this row space is orthogonal to null space. That's the claim. Here you can see that. So this row space is orthogonal. So here we have this 90-degree angle. Is it clear?
Yes, sir.
Okay, so this is clear. So similar argument can be extended for this column space. So column space will be also orthogonal to this null space of A transpose, that is left null space. So this will also be orthogonal to this. Okay, can I stop here for a bit? Maybe I'll drink some water. I haven't drank water, so I'll just get water and I'll give you some 3 minutes break. So what we were up to is that we wanted to see, I wanted to show you that this row space is perpendicular to null space that I showed you. I said that symmetrically what you can do is you can do the similar thing for this. You can do the similar thing for this column space and null space. That's how you can show these things are also orthogonal to each other. So now we know that these vectors are orthogonal to each other. Is it clear? Is the orthogonality between these subspaces clear?
Yes, sir.
Is it clear? Nice. Now I can write this row space is orthogonal to, so I'll write these two statements so that it gets sort of ingrained. Row space is orthogonal to null space. The other thing that I'll write is column space is orthogonal to left null space. You saw there are different beautiful properties in here. So first thing, that is they are perpendicular. I'll just paste this. So this is the thing that I wanted to paste. So here it is. So about these subspaces. Now if you see that if you add the dimensions as well, so if you add this r plus n minus r, you will get n out of this. So that's how why these vectors belong. If you again do the similar operation for this, m minus r plus r, so you will get m. That's where these vectors belong. Okay, so there are beautiful things in these four subspaces and they're also at 90-degree angle. So each vector has basically 90-degree angle with other vector space. So that's how these vector spaces are orthogonal to each other. Should we take an example to? Okay, let's take an example. Let's suppose we have this vector 1, 2, 5. Okay, let's suppose this is a vector. And then we have x1, x2 and x3. Something like this. Let's suppose this is equal to 0, 0. This is like that, ax is equal to 0. And we want to show basically null space. So null space of A, so null space of this A and column space of A. So if you take null space of this, column space of this. So what is the column space of this? So any vector C multiplied by this whole vector. So C multiplied, if you want to take column space, so this vector and then this vector multiplied by anything. Let's call this C1 multiplied by 1 plus C2 multiplied by 2 plus C3 multiplied by 5. So these vectors will be in the column space. Okay. In the row space, what I'll have in the row space, I'll just multiply any C with whole of this row. So any row of this format will be in the row space. So what will be in the null space? So in the null space, I'll make sure that I'll get these zeros. So that's what I have to show in the null space. So I'll have to show that 1 and x1 plus 2x2 plus 5x3 is equal to 0. This is what I have to show for null space. I multiplied this with this. Okay, and multiplied this. This should be 0 basically, just one equation. So this multiplied this with this, multiplied this with this, and I should get 0. So any vector possible here is, yeah, so we can just get value 1 x1 and then for this x2 we can give value 2 and x3 1. 1 2 1, it belongs to null space. Can I see that with this vector 1 2 1 belongs to null space? Why? Because if you take 1 2 1 multiply this, that is 1 1s are 1 plus 2 2s are 4 and they should be minus 1, let's suppose, and then 5 1s 5. So this is 0. Okay, so 1 1 2 minus 1, it belongs to null space of A. Okay, a simple vector that belongs to the row space is 1 2 5. 1 2, 5, this vector belongs to column space of A. Sorry, row space of A. And now I have to show you these are perpendicular. So just multiply this. 1 1s are 1 plus 2 2s are 4. 1 1 minus this 5. So this is equal to 0. So I just have convinced that I showed you by example that if you have this vector 1 2 minus 1, that belongs into the null space of A, and then we have this vector 1 2 minus 1 which belong to the null space. Okay, then we took this vector 1 2 5 which basically was in the row space of A. Okay, if you multiply them together, this vector multiply by this vector, we'll get 1 plus 4 minus 5, that is equal to 0. This is what we got out of this. So these two vectors are orthogonal to each other. So I just showed you an example to prove the orthogonality, and similarly you can take the other things. Now they are not just perpendicular, they are not just orthogonal, they are orthogonal complements. So what I can write is I'll write null space and row space. They are orthogonal complements. They are orthogonal complements. Okay, they are orthogonal complements. That means null space contains all the vectors. So null space contains all the vectors that are perpendicular to the row space. Whatever vectors are there which are perpendicular to row space, null space has those vectors. Okay, that's why they are called as, they are complements, orthogonal complements. In maybe let's suppose in Rn, because that's where these vectors belong in. Let's say if you give me any vector, so if you say how many vectors are perpendicular to this particular vector, I'll say all these vectors belong into the null space. So that's why they are called as orthogonal complements of each other, because any vector in the null space is basically perpendicular to this. So there are different vectors which are perpendicular to this row space. So I'm saying all of these vectors basically are in null space. Okay, so null space contains all the vectors that are perpendicular to the rows or row space. Is it clear? Why are they called as orthogonal complements? So there is a little bit distinction. The distinction is that orthogonality means that every vector should be perpendicular to each other. So but here there is a distinction that there are many vectors in row space, and there are a lot of vectors which are perpendicular to this row space. I am saying that all these vectors which are perpendicular in the row space, they are present in null space. And similar for the null space as well. All the vectors that are perpendicular to the null space, they are basically in the row space. That's why they are called as orthogonal complements to each other, and that particularly in Rn because these vectors are in Rn. So it is like this. So one vector will be a plane. Let's suppose a column space is a plane, and then this null space may be a line of vectors. Okay, so here you see that any vector you take, it will be perpendicular to this vector. Any vector you take in this plane. So this is the plane. Let's suppose we have the column space is plane. Let's suppose this is our column space. It's a whole plane, and then this is our null space. Let's suppose a vector of lines is our null space. So you see that you take any vector in here, you take this vector, this, any vector in this, so it will be perpendicular to this, it will be perpendicular to this blue line. So that's why these are called as complements of each other. So they are complements in Rn, orthogonal complements. Is it clear? Is it clear? Nice. So now coming back to the solution. So we are trying to solve Ax is equal to b for which there is no solution. We are trying to solve Ax is equal to b for which m is greater than n. Again going back to the problem of linear regression. So here we have the number of equations is greater than the number of variables. That's what we want to solve. And for this what we are trying to do is we want to solve this Ax hat is equal to p. Just let me tell you upfront what are we going to do. We are trying to actually solve something called as A transpose Ax hat is equal to A transpose b. This is what we are going to actually solve. And now we'll see where to get this part. Where to get this part from. Okay. So our problem in the linear regression, if you saw, it was to solve this thing. But we know that the solution won't exist because you know that this b may not be always in the column space of A. For that, what we did is we said that we'll take some vector x hat, which will give us some vector p, which will be in the column space of A. That's what we'll try to solve. Now I'm telling you that this solution somehow comes from this equation. So I'll get this A transpose A and I'll get somehow this equation. So what is the beautiful thing about this A transpose A? Let me tell you this. What is the beautiful thing about this A transpose A? If you see, this is a symmetric matrix. What is the meaning of symmetric matrix? Anyone? Amir, what is the meaning of symmetric matrix?
Yes, sir.
I
मतलब कि
lost
जो
you in between. I lost you in between. Can you just again go? Rian, your voice is not visible. Your voice is not audible. Sorry. Rian, I'm not able to hear you at all. Can you just mute yourself? Amir, you are saying something, right?
सर जो रोज होगी मतलब कि इसकी मैट्रिक्स ए की वो उसके कॉलम्स में
Column,
हो
that
जाएगा
basically
मतलब
means A transpose is equal to A. This is the meaning of symmetric matrix. That is Aij entry is equal to Aji entry. So what's the meaning? What is the example of symmetric matrix? This is a symmetric matrix. So if you just transpose rows and columns, you will still get this 1 2 2 1. Okay, or maybe 1 8 also. So similarly, this will be also a symmetric matrix. So in here I am saying this A transpose A will be symmetric matrix. That means A transpose A whole transpose. It will be basically mathematically, I told you that A B transpose is equal to B transpose A transpose. So this will be equal to A transpose A transpose transpose. Just giving transpose this first and then giving this. So that's how I wrote it. So A transpose is again A. So this is basically the same thing. I proved it mathematically like it's symmetric. So this is a symmetric matrix that you have to see. Now that's what our job is basically to get this matrix. Now we'll see how to get this matrix. But make sure that this matrix looks like this. For let's take an example, something like this: 1 1 1 some 1 2 6. Let's suppose this is our matrix A. So how to compute A transpose A? So A transpose A will basically be equal to 1 1 1 1 2 6. This is A transpose, and then multiplied by A 1 1 1 1 2 6. Okay, so how to get these things? So we can either take the linear combination of these things. So it will be one time of this, one time of this, and one time of this for the first column. So it will be 3 and 6 to 8 9, and then the other one time of this, 2 time of this, and 6 times this. So this, let's suppose, is 1 times of this. It is let's do it in the original form. So this will be, let's suppose, 1 2 6 6 2 8 9. This will be 9. And now we have to figure out what will be this. 1 1 is a 1, 2 is a 4 5 6 36 36 5 30 41. So this is what we'll get. Okay, so do you see that this is a symmetric matrix? Do you see that it's a symmetric matrix? Okay, so one more thing I'll tell you, this is a symmetric matrix, so this matrix is symmetric. Okay, and on top of that, if it is invertible, so if it is invertible, basically the inverse exists. So how will the inverse exist? So for this A transpose A, take the word from me, the inverse will exist if all the columns in A are independent. Okay, so what I'm saying is that the A transpose A inverse won't always exist because there can be dependency in the rows. The inverse will exist if the columns of A basically are independent. Okay, so I'll just write this. So A transpose A is symmetric matrix. A transpose A will be invertible, if and only if basically is if you have read about these logic, proportional logic. Maybe sometimes I'll tell you what's the meaning of this. So if A has independent, I'll just write if, not if and if, because both conditions may not be equal. So A transpose A will be invertible if A has independent columns. And for you guys, it will be an assignment question. Probably you'll have to prove it mathematically. So this will be an exercise problem for it. It's not difficult to prove it, but I want you to learn the skill of how to prove these things. Okay, now the question is, going back to linear regression, our problem was to solve this Ax is equal to b. I told I'll solve something like this. How I'll solve? I'll get this. In order to get this, now we are going to the next topic, that is called as projections. Just see how I'm connecting all the things, and at the end we'll be just putting these puzzles together to solve the problem of linear regression. Okay, we still have some time left and I think it is doable. So now we'll see next topic, projections. This will be the topic. Is it clear till now? Is everything clear till now? Orthogonality,
yes,
orthogonality of subspace, is it clear? Nice. So what is the projection? I also covered this projection. If you see the first lecture, I covered it. Now I'll generalize the concept of projections here. So let's suppose we are in some vector space, and let's say we have a subspace. Let's call this A. We have the subspace A. Let's suppose we have an other vector. Say this is vector B. Okay, this is vector B. Now you know that, let's suppose I have some vectors. For this I have some basis vectors for which this B is not the solution of. Maybe I'll tell you this story afterwards. First let's focus on the projection part only. So projection basically means you are dropping some torchlight in this direction, so that if you draw a perpendicular here, okay, so a shadow will be formed over here, a shadow. So this part over here, so this over here is called the projection of B onto A. Okay, so this is what is called as projection of B onto A. Let's suppose this projection is point P. This is point P, this is the projection point P. So how I can write projection? Projection basically is some x multiplied by A, because it's in the direction of A, and it will be some multiplier of A. So am I clear with this? It will be are you okay with this? Like this P will be basically some multiplier x multiply with the A, basically the direction of A. Is it clear?
Yes, sir.
Okay, so if you are convinced about this, now we want to find, so what is the value of projection? Before this, I actually gave you this as an assignment problem, like exercise problem. Now I'll do it on my own, and then we'll generalize it to ND case. So this is just in 2D projection. So this basically lies in R2, and this vector also lies in R2, and we want to see the projection. So if you see, let's call this error E. So this will be B minus P. So this will be B, and this is P. Okay, now you know that this B minus P, it is basically perpendicular to A. So this B minus P, or we can directly write E is orthogonal to A. This I can write. So this over here is E, and this is orthogonal to A. So this is E is equal to B minus P. This is this vector, this much. This is E is equal. So I can write it mathematically like this. I can say A transpose B minus P is basically 0. That's the meaning of orthogonality, isn't it? Isn't this the meaning of orthogonality? If these things are perpendicular, so I can write it like this. That basically means A B minus P is equal to 0. I can write it like this. I'll just expand it. So this will be A transpose B, and maybe I can also write this P is equal to XA. Now this projection, this point is some projection P, so I'll write it as XA. So I'll write A transpose, just expand like this, B minus some X multiplied by A is equal to 0. I just gave this projection value, which you agreed that this P should be basically equal to some X and multiplied by A, basic direction. So this will be A transpose B is equal to, if I just take on the other side, so it will be A transpose AX. Is it clear? Is this much clear? Is it clear? This one? Just look at the equation, how I derived it. So now I can just say I have to find this value of X. So this X basically will be equal to A transpose divided by A transpose A multiplied by B. This is the X. Now if somebody tells me what is the projection P is equal to this X multiplied by A. So we have this projection, let's call this projection PROJ. This is equal to A transpose divided by A transpose A B and multiplied by A. Let's write the A over here. Okay, we can just stick it in A here, right here. Okay, so do you agree that this is the projection? This is how we define projection. Because if you see the initial lecture, I also gave you the formula like this. Now what I can say is, if you see this A transpose A, okay, A basically is, if you see this one, A transpose A. So what will it be? A transpose A divided by, I think it should be A transpose. Oh, sorry, it should be A transpose, because we have X multiplied by A. So it should be A transpose here, over here. Should be A transpose. Because in the middle, if you when you multiply this X with A, so X will remain as it is. So this will be the multiplier at the front. So this will become A transpose, if you see this. So this A transpose is a matrix. It is basically an outer product. This is the rank 1 matrix. Why is it rank 1 matrix? Let's suppose I have a vector 1 2 3. So if I have A multiplied by A transpose, that is 1 2 3 multiplied by 1 2 3. Now this has 3 cross 1 and this is 1 cross 3. Now I'll get a full-fledged matrix 3 cross 3. But you know that each row will be dependent. So in the first row it will be 1 2 3. In the second it will be 2 times of this, 2 4 6. It will be 3 times this, 3, 6, 9. So all of these rows are dependent on each other. So only one row is the basis. That's why I'm saying it's a rank 1 matrix. Rank 1, why? Because only one pivot will be there when you reduce it to row echelon form, because all these rows are dependent on, all these columns are dependent on each other. So this AA transpose, whenever you see a vector A and AA transpose, this is a rank 1 matrix now. A rank 1 matrix. So now you know that this part, this portion, this will be some constant because this is a dot product. This will be one scalar value. And on the upper side, here we have a matrix. So matrix divided by scalar is also a matrix. So this projection matrix, we can just write it like this. So we have a projection matrix. Projection matrix. So how is it like? This projection matrix is AA transpose divided by A transpose A. This is our projection matrix. Is it clear? Is this thing clear? This is our projection matrix. So now we'll just extend this case to our n-dimensional case. Now here you saw that we had just this vector, like this was in 2D, and we had to just basically plot a point. So if we have to sort of see this, now let me tell you about something about the projection matrix first. So this projection matrix, now if we see this, so this is our projection matrix. So the first thing is this projection transpose will be projection. Okay, as we saw that if we have a matrix AA transpose, that will be this will be symmetric. Okay, I think I took A transpose A, I guess, if I am correct. Let me see if it is. But take this. Will it be symmetric, this part? So let's just erase this portion. So here, will it be symmetric? Because A transpose, it is a full-fledged matrix. Okay. So if you again do the transpose, same, you will get the similar thing, because AB transpose basically is equal to B transpose A transpose. Okay, now we have AA transpose, so whole transpose. This basically will be A transpose transpose, AA transpose, and then we have A transpose. This will be AA transpose. So is this clear that this will be, this matrix, projection matrix will be again the symmetric matrix? Are you clear with this?
Yes, sir.
Just look at the equations how I did it. This will be a symmetric matrix. I told you that A transpose A also is a symmetric matrix. Here, this also is a symmetric matrix. This projection matrix is also a symmetric matrix. One more thing about this projection matrix. So the projection matrix is symmetric. That is for sure. This is symmetric. So one more thing that is about this, if you take a projection first and then you again take a projection, that basically P square, it will be equal to P. Okay, what is the meaning of that? The meaning geometrically is, so if you take the projection of this B onto this space, onto this line A, okay, you will get this line, which I'll maybe draw with this. This is the line, this is the projection line. If you again try to project, so here now the projection will be basically the same line. You can also mathematically prove it. Okay, you can just square these things up and maybe it's easy to prove. I don't think it's difficult to prove. So this A transpose, if you again took this A transpose A, just having the scalar, it's a separate thing. The scalar is a separate thing. So here we'll get, so you'll have to put a bracket in such a way so that, okay, I think if you guys just take an exercise, otherwise it will again take me some 2-3 minutes to prove it. Just take an exercise, but I think you guys can prove. Just square the matrix and you will easily be able to get the value of this P back. So you have to get the value of projection matrix back. You have to square this number. Square this, basically multiply it 2 times. So that means this is A transpose square. So that means this is A transpose into square, basically means transpose the first part. This should be transpose, then A transpose. I'll leave it here, and now you'll have to expand this. You'll again get back this A transpose value. So the two important properties that I want to mention here is, the first, this projection matrix is a symmetric matrix. Then if you apply the projection matrix twice, you'll get back the projection matrix. Is it clear? Are these two properties clear?
Yes, sir.
Now the question is, why to project? The question now remains that why should we project? Why to project? That's a question. Now this question will be again linked with the linear regression that we started. Now we had points like this. So one point was like this, one point was over here, and one point was over here. And we were trying to fit a best line. So let's suppose this was the line. Now what we will do is, we'll just have the projection of this point over here. Let me just not have this crosses so that this diagram is clean. So I want to make this cleaner diagram. So let's suppose we have one point over here, we have other point over here, and we have some point over here. These are the 3 points, and we want to project them because we want to minimize the error. So this is the error and this is the error. Okay, so this is our projection. So this point, which I'll just mark with blue, this is our projection point for these points. So what are these blue points? So these blue points are projection of red points, projection of red points onto this line that we fit onto this line. Let's call this line L. Do you see why do we need to project? For example, if you have the points, because we are trying to fit the line, and now we have this errors. Let's call this error E1. This is our error E1. This is our error E2. This is our error E3. And we want to minimize the error. What is this error? So basically, if you see, if I just write this equation, maybe I'll write the whole equation when we'll solve this least squares. This is called as least squares problem. But just know that this is the whole point. The point is that this solution is not existing, and now we try to fit a line. Okay. This is why we need to project. So I gave you the answer. Why do we project? And now slowly we are building towards the solution of linear regression. I don't want to give every piece at once because it will be too hard to digest that way. So is it clear why do we need to project? Is it clear?
Yes, sir.
Because we need to minimize these error, and just have this diagram in the mind, and we'll visit this diagram multiple times till we sort of clear whole of this regression problem. Now let us generalize the projection of these points onto subspaces. Let's suppose I'll just make again a thread. Let's suppose this is a plane and we have a plane like this. Let's suppose this is a plane and there is some vector which is out of this plane. Okay, let's suppose this plane is defined by two vectors a and b, or maybe a1 and a2. Okay, this is how it, let's suppose these two are the bases, because you know that plane is defined always by bases. So what the basis vector that span it. So now we have this ax is equal to b. So what is the vectors in a? So in here we had this a1 and a2, and we want to find such axis so that this is equal to b. Now you saw that this b is out of the plane. This b is not lying in the plane itself. This is not in the column space basically. This is not in the column space of a. So what to do now? We'll project it. Okay, we'll project it onto this plane. We'll project it onto this plane. Okay, so that this b will become some b dash. Okay, so this projection will become some b dash, and for that let's call this projection as p. Let's suppose this will be the projection onto the plane. Let's call this projection p. Let me make a better diagram. So this is a1 one basis. Basis can be anything. And now when you project this onto the plane, let's call this is the projection. This is our p. Let me just make it a little bit bolder. So this is our projection p. Do you see that this is our projection now? Because this b was not lying on this plane. That means this was not lying in the span of this a1, a2. This is the matrix that we had. This was not lying in the column space of a. This was not belong. This b was not belong to this. So b that did not belong to this. Now what we are doing is we are projecting p. So we have this p. So p is a projection of this b. It does belong to column space of a. Okay. Now we want to find the projection. Okay. So how to find this projection now? Let's see that. Okay. So how to do this projection? So the projection will be something like this, because this vector p again can be represented by this a1, a2. Let's suppose it will be represented by this vector p will be represented by some x1 a1 plus some x2 a2, because now this vector p, it is in the span of a, it is in the column space of a. So we will multiply this a1 with some constant, multiply this a2 with some constant to get this p. Okay, so even I can write it like simply. If I want to write it, I can write like this, a into x. Okay, so this is p. How I? Because I'll just collect these, a1 is like this, a2 is like this, and then we have this x1 and x2. Okay, this is what I will write. Okay, now these x's are basically had because this is the projection. It is not the original x. This is x. I wrote this in the succinct version. This equation I wrote in the succinct version as a is equal to ax. Is it clear? Is this much clear? I don't want you guys to lose the details of these things. So is it clear?
Yes, sir.
Because what I'm telling you is that this p is now belong to the column space of a. If it is belong to the column space, that means I can take the linear combination of these basis vectors and compute this p. So I'm taking the linear combination of a and a2, a1 and a2. This is what, and that's represented by p. Now you know that in the succinct version, or in a keyworded form where we can represent a shorthand notation, I can just write this matrix A like this, and I can write this matrix X hat like this, and this will be represented like this in the linear algebra form. So the key thing that is here, the key thing that is this B minus A, this one, this vector over here, this vector over here, and this basically is B minus P. Again, this error vector B minus P, it is perpendicular to the whole plane. Okay, it is perpendicular to the whole plane. So what is this B minus P? So B minus P basically is B minus AX. Okay, this is perpendicular. This B minus AX is perpendicular to plane. So do you agree with this? So this, let's show it like this. Let's suppose this is my iCard, and here we have, this is our plane. So here we have a vector like this. So this pen basically is perpendicular onto the plane, and now the length of this pen is B minus P. Now we know that P is equal to AX. P is equal to the combination, linear combination of the columns of A matrix. So this is perpendicular to it. That's why I wrote this B minus AX is perpendicular to the plane. Is it clear? Is it clear how is it perpendicular to the plane?
Yes, sir.
So that basically, how is plane represented? Plane is represented basically by this A1 and A2 transpose. So what I'll do is I'll write A1, that is the column vector. I'll write A1 transpose. If it is perpendicular, A1 transpose B minus AX hat is equal to 0. Can I write this? Because yes, because it's perpendicular. It's perpendicular basis. So I can just write plus A2 transpose B minus AX. That's also equal to 0. So I can just plus it and write them equal to 0. This is equal to 0. Can I write it like this? Do you agree? I can write it like this.
Yes, sir.
Are you do you agree, Dhyan, Jahangir? Do you agree I can write it like this? Because I told you that this B minus AX is perpendicular plane. The plane is represented basically by A1 and A2. So it should be perpendicular to both of these vectors. So that's for how I wrote it. So I will write this also in succinct way. So how I can write it? I can write A1 transpose A2 transpose multiplied by this B minus AX. This is equal to 0. Okay, now this can be represented by whole A transpose. Let's call this, so this will be 0 0 basically. Okay, so now what I'll write is I'll write this as A transpose. This basically is a matrix. I'll write it A transpose. Okay, and B minus AX bar is equal to 0 0. Let's just write 0. How many zeros are there? So now you know that this belongs to the null space. Okay, for this A transpose, because A transpose X, if it is equal to 0, that means the vector X belongs to the null space of A transpose. So that means this B minus AX, it belongs to the null space of A transpose. What is the meaning of that? So if you again see those pictures, this is really important. Now to understand this, this is a really crucial portion of this. So what I'm saying you is that, so we had A transpose basically this row space. Okay, so if a vector is there, if a vector, let's suppose some vector is there, some vector B is there over here. Okay, so the projection we are projecting onto the row space. Okay, we are trying to, because this is the row space, A transpose now is row space. So this is the projection of this vector is P. This vector is P. Okay, this is the portion of vector. And what I'm saying is that this P minus AX, for example, it belongs to null space. So something belongs to null space over here. So some vector over here belongs to null space. Let's call this as the vector, and this is the value of that B minus AX that belongs to null space. If you see this B minus AX, so this B minus AX is this vector. So this is this vector B minus P, that is error vector, the error that we are getting. So the projection basically belongs to row space and the error basically belongs to null space. Do you agree with this?
Sir.
Do you agree with this? Because we are trying to project. That's why we are trying to project in the row space, because A transpose is there. So here we are trying to project it onto these things. So it should belong into this. Okay. Then what we saw is that this error vector, basically the error that we are getting out of that, if you remember that that line of the linear regression, that basically belongs to this null space. Then there are two pictures now going on. The first picture is this. The first picture is this one. This picture. That's the first picture you have to keep in the mind. So this is the projection there. And then if you see this E error vector, the other picture, in there you have this P, this belongs to row space, and this E basically belongs to null space. And this is clear from this equation. This equation. So what is our equation? Our equation is A transpose B minus AX hat is equal to 0. Now what are we up to? We want to find this x, we want to find this projection, because we know that this projection is equal to ax. Okay, ax hat. So we want to find this x basically. So now expanding this equation, this will be a transpose b minus a transpose a x hat is equal 0. A transpose b, this is equal to a transpose a x hat. Is this much clear? Now you know that why to solve this 8. I told you that we have somehow we will get this equation. Did you saw these equations? I told you when we'll be solving linear regression, what we'll get? We'll get this equation if that is written somewhere. So what I have written that? I told right here, I think. Yeah. Did we reach the same point? Yeah, that's what we have to solve for the linear regression. Now if we want to find the x value of this x bar, so what will be the value of this x hat? This x hat basically will be equal to, just take a transpose b divided by a transpose a. This will be the value of x. So if I want to find the projection matrix, so first I'll see the projection. The projection basically is a transpose b divided by a transpose a multiplied with this a. If you see this a, let me write it with the blue. Okay, and this portion I'll call this projection matrix now. The projection matrix in any dimension is basically a transpose divided by a transpose a. Now this we cannot write it like this. Why? The problem here, it's not a number, so we should write it in the inverse format, because this itself is a matrix. So I will write it like this: a transpose a inverse. So we can write it like this, like simply we can write it like, because this can't be written in numbers like this, so I'll just, this even can't be written like this because these are not numbers. So what I'm trying to tell you that this is a transpose, and this should be written as a transpose a inverse, because this is the matrix itself. Okay, this is not a number anymore. In that a transpose a, it was a number. Now this is a matrix, so we'll, instead of dividing it, we'll just write its inverse. This is a inverse a and multiplied by b. Okay, this projection now becomes a transpose a inverse multiplied by a and b. This should be whole inverse. Now what I'm saying is this much is the projection matrix: at a transpose a whole inverse multiplied by a. So this is our projection matrix. Is it clear? Is the fact clear that why did not divide it, why did I multiply it, like why did I write inverse? Because this is not a number now, this is a matrix. Is it clear? Just look at
Yes,
it.
sir.
So I'll just wait for maybe 20 more seconds, just look at this equation. And you know that this E, basically E belongs to that error vector. It belongs to null space of A transpose. Okay. And this E vector is perpendicular to column space of A. These are the two things that you have to remember. Okay, this E vector belongs to null space of E transpose. So I think I wrote it wrong. So it should be in the here. So it should be basically in the other way around. It should be in here. This is R vector. So this is our column space. So this was its, and this is the E vector. This is our projection, this is our E. Okay, the same basically same follows, but not in these two, in these two basically. This E should be perpendicular to null space of A transpose. That's what I wanted to show, because that's what equation told us. Equation is this. This basically lies in A transpose. That's why this belongs to this null space of A transpose. Okay, is it clear? I just made a mistake over here. I did not see this row space and null space, because this belongs to NTI, this N A transpose. So that's what this equation says. Because AT x is equal to 0 basically means this x belongs to null space of A transpose. That's what I'm saying. This error vector belongs to null space here. And you know that this is perpendicular column space. That's what I have written here. This E is perpendicular column space, and this E belongs to null space of A transpose. Is it clear?
Sir.
So can you ask me a question over here? You can ask me like, why don't we just invert this? Because as we know that if you apply this inverse over to these, so this will be, for example, A transpose. If you have A transpose A whole inverse of A, so we can just invert it basically. If we invert it, so if we try to invert this whole inverse, so what we get is So if you know that A B whole inverse, I think is equal to B inverse A inverse. So I can write A transpose, this is equal to A transpose inverse, A transpose inverse, and A inverse, let's suppose A inverse. So this will become basically equal to I. Okay, so this should be basically equal to I. So why can't I do this? So have I done anything wrong? I think this should be A transpose and A should be here and there. So this A should be over here and this A transpose should be here. Just check these equations. So that's the reason I have to check it. This is A transpose basically, yes. So this should be the inverse should be first, and then we should have this A transpose and B. Similar for this. This is the projection matrix. Just look at these when I'm solving this, like make sure where to put inverses. So basically I think this is the equation of the projection. So A transpose A inverse, then we have this. So what I'm telling you is that why can't we directly apply the inverse and this whole thing will become identity. This whole thing will become identity. So do you see my point though?
Sir.
Do you see my point is that the first thing, like again coming up, so this projection matrix, if you again see it from here, so we got this A transpose AX basically was equal to this is the thing that we got, A transpose B. Okay, so now after doing this, I have to apply inverse on both sides. Okay, to correct my mistake that I have previously committed. So I'll write X transpose, that's basically equal to A transpose A whole inverse multiplied by A transpose B. That is the value of this X. So now I know that this projection basically is equal to AX. Okay, now I have this value of X. So what I'll do is P is equal to A and put the value of X, that is A transpose A inverse A transpose. This is my projection matrix now. Is it clear?
Yes, sir.
Okay, this is what I wrote for the projection. So because B, I'm keeping the B separate. So what I'm telling you is that if this matrix is invertible, as you know that this A B inverse, this is equal to B inverse A inverse. So can't I do it like this? So it is A, I'll write A inverse. So I'll write A inverse, then I'll write A transpose whole inverse and A transpose. So this thing will become identity and this thing will become identity. So isn't this whole equal to identity? Is it? What do you say? Is this whole equal to identity? Rian, yes or no?
Yes, sir.
Salim, Rian, what do you say? Is it equal to I?
I think, sir, it is.
This basically is not equal. Why? Because this is a rectangular matrix. This is not invertible always. So this A transpose, we said that sometimes M can be greater than N. This is an rectangular matrix and rectangular matrices are not invertible. So that's why I wrote like this. So if it is a square matrix and if it is invertible. So for the invertible, if you remember that I told you, if A has independent columns, then this A transpose A is invertible. As a whole, it's invertible. But if this A is rectangular, how can it be invertible? This is not invertible at all. So we cannot write it like this. We cannot write A inverse because it's not invertible. We cannot write A transpose inverse because it's not invertible at all. So the projection matrix is over here. So but if it is square matrix, but if this A is square matrix, so that time we can say that if it is square matrix, that time it is inverted. It is equal to I. That basically, if it is square matrix, that basically means you are projecting on the space in which the column also belongs. It basically means like this. If you have a plane like this and you are trying to project this B onto the same plane and it exists, so that time I'll say that the projection will be equal to I. Nothing will happen to projection. B will itself lie on that. The projection will be like this. Is it clear? So last statement I think is a little bit ambiguous for you. What I'm saying
Yes,
is
sir.
that I'm saying if this B belongs to column space of A, that means it is invertible. Then that means that whole transformation is invertible because we are able to get this B. So that means you don't have to apply any transformation and any apply projection. That projection basically will give you the value I. That's why I'm saying if this A is a good matrix, an invertible matrix, that time this projection will be equal to I. Is the concept of projections clear? Again,
Yes,
we can
sir.
see the same thing. The projection matrix, I'll write like I have a strong urge to write it because I have to again show you the two properties. So this is equal to A transpose, A whole inverse, A transpose, something like this. This is our projection matrix. So I told you that pt is equal to p. Can you just transpose it? If you transpose this one, you'll get p back. I told you that p square is equal to p. So you can just prove these two properties onto this. I think it is easy. So I'll just show you this p square wala thing. So how to do this? So this basically means, so if you apply this p square twice, so you'll just apply a and then a transpose a inverse and then this a transpose. This is p square. This is p and p. This is p square. So what to do now? How to put the brackets? Put the brackets in such a way so that this becomes invertible, right? Huh? So put these two brackets over here. Okay. So I'll just remove these brackets. This is a. And then what I'll do is, right. So because this and this becomes identity, if you see, this is inverse of this, so this becomes identity. Okay, so this becomes identity as a whole. Let me just write it again so that there is no mess. What I'm saying, you just write it again. A, so this is our p, first p. So I'm writing this a multiplied by a transpose a whole inverse. So and I'm writing a transpose. This is p multiplied by p. So I'm putting the brackets in the right places. So I'm saying put one bracket over here. Okay, because this thing and this thing now becomes an identity. Okay. So now when you sort of again get this a transpose a inverse, now you again get this p back. Did you see this thing and this thing cancelled out? So we got a transpose a inverse a transpose, again the p back. So I just showed you this property. I think this is really easy to show. Is it clear? Is it clear?
Yes, sir.
This is
Yes,
how
sir.
I showed you the projections. Okay, so I think we are out of time. So in the next lecture we'll see how to solve. Now we have all the equipments. Now we only need to put these equipments together. We have all the pieces and we need to just fit these pieces together to solve the problem of linear regression. Okay, this is what the problem that we have to solve, and this is sometimes called as problem of least squares. I'll tell you why it's called the problem of least squares. Okay, was it clear so far? Maybe I'll just stop recording and I'll ask you regarding the doubts if you have any.